didn't meet him is from the University of Bologna, is doing the postdoc there. He did the bachelor and master degree in Roma, Sapienza, and the PhD in Manchester. Is in the LHCb collaboration since 2013. I studied it, and and is working on elective universality and spectroscopy, simulation. So we will talk about spectroscopy today.
Yeah. So I'm going to give you hopefully not boring review on what exotic spectroscopy is, why it is important, why it's fun, and why we study it, especially at LHCb. So this is just a short summary of the talk. So I'm going to start with what a charmonium is, and especially what the spectrum of excitation of charmonia is. Then on to what an exotic state is, why is it interesting to study, and then just a couple of specific examples of exotic states. So this is the most famous one, probably the X3872, and then charged exotic states, tetraquarks, pentaquarks, and all the most recent results that we have, especially from LHCb. Okay, so let's start with the charmonium and what exactly is a charmonium. So basically, we can describe the excitation spectrum of a c-cbar state, where Q in this case is a heavy quark, so charm and bottom, with this semi-relativistic phenomenological potential, which is called the effective Cornell potential, and it has three different terms. The first one is a short distance collar potential, then a long distance confinement term, and then corrections for spin-spin and spin-orbit interactions. And this was developed in the 70s, and it was found to be particularly accurate to predict the full excitation spectrum, especially for the c-cbar system, and which is called the charmonium system, and the b-bar system, which is called bottomonium system. However, in the last 15 years, a large number of states has been discovered, which actually contain a c-cbar pair, but they don't exactly fit in the spectrum described at this potential. So let's go and have a look at what this looks like. So this is the charmonium excitation spectrum as of beginning of the 70s. There's just nothing. And you might know that the first one discovered was a GFAE by both Slack and Brookhaven in 1974. And from the GFAE, you can apply the Cornell potential and just find a full prediction of all the states of the c-cbar system. And actually, this is more or less what we observe. So this is, for instance, some of the states that have been observed in the years after the discovery of GFAE. We have a lot of the psi column here, the ground state eta c, the first orbital excitation, which is the KC1, KC0, C1, and C2. And this is more or less what the charmonium spectrum looks like today. Just this state here, the psi 3 1D, was discovered last year, just to give a bit of context. But this is not really exactly what the charmonium excitation spectrum looks like, because there's also this guy here. Okay, this is what we call an exotic candidate. I'll tell you why in a second. Its mass is quite close to this predicted state, but there are a few properties that don't fit in the c-cbar predictions. So this is not exactly what the spectrum looks like. This is more likely, and so there's actually a lot of this states discovered in the past 15 years. But again, this is not what it looks like. This is more like it, okay? Because there are also a lot of charged states which cannot definitely be c-cbar. There must be something else. And again, this is not exactly what it looks like. And this is more like it. And we also have these new states that they were discovered in 2015 by LHCb. I will talk about that later. And this is, as well, not joking, this is now more or less what it looks like. This might be not 100% updated, but maybe a few states missing. But you can see that a lot of the states that were discovered are actually they don't actually fit in the predictor spectrum. So why are we interested in those states? Because those states are what we call exotic states. We call them with this X, Y, and Z letters, which is actually an obsolete naming convention. The X3872 is actually called the KC1 3872 now, but we still use X, Y, and Z for pragmatic purposes. And they must contain a c-cbar pair, as they all decay into a final state with charmonium, usually a GFAE, not always, but usually GFAE. But they don't present the same properties expected from c-cbar states. That's why we call them exotic. And depending on the specific particle, there might be one or more of the following things that don't fit. So, for example, the mass could be far away from the predicted mass of the given state. They might have narrow width above the open charm threshold. So when you go above the open charm threshold, they are expected to decay into D mesons with a large phase space. So the width should be large, but usually, well, some of these things have a very narrow width. Then we have predictions for radiative decays, which don't match. A couple of them decay into states with different isospin, so there's isospin violation. There's a large production cross-section, which is not predicted to be as large. Some of them have non-zero electric charge, which is clearly nonsense if they are c-cbar states, and they might have unconventional JPC assignments. So they are usually studied as multiquark candidates. So you might have heard of tetraquarks, pentaquarks. This is where it all started. So what are the models that we use to describe multiquark states? Well, there are mainly three. The first one is the mesonic molecule or baryonic molecule, according if there's a 4-quark or 5-quark state. This is a very interesting model, but it predicts states with low binding energy, which means that they are narrow and they can only be S-wave because the energy is not enough to have relative high angular momentum. And the interesting thing is that their components can decay independently, okay, this and this. So this could explain isospin violation, for instance. And the mass of the molecule has to be closer to the two-body threshold, a little below, okay? Just like any molecule in the real world. Another interesting model is the compact multiquark model. So that's the compact tetraquark or compact pentaquark. In this model, you actually have tightly bound states. So the binding energy is very high. And basically the main difference with the molecule is that the q-bar system here is a color singlet, while the q here and q-bar here is a color triplet. So in this case, they can actually interact with gluons. So they're very compact. They can have large prime production cross-section, especially a high PT. But of course, being two triplets here, you have a full isospin spectrum. Okay? So many isospin partners are predicted, but none of them have been observed so far. Then the hydroquarkonium, this is the the weakest model we have up now, in which you have a q-bar, so a true charmonium surrounded by light quarks. There's no requirement on the mass, but it's not clear whether this thing can actually happen. So if the binding this is unclear in the literature, or you can just have a mess, just 4 quarks interacting in non-linear way. And in this case, if you study that, you have made poor life choices. Then this is just something that we use all the time to study this. It's called the Dallas plot. I suppose many of you know what it is, but in case you don't know, I'll just tell you again. This is a powerful tool to investigate 3-body decays, where you just plot the squared mass are two particle system here, and the square mass of the other two particles here. And this basically exploits the fact that the total decay amplitude is dominated by a coherent sum of subsequent two-body decays. And in this case, you can actually see the intermediate resonances. So this is a simulation, for instance, of a non-resonant decay, which everything is flat, or a decay that goes through F0, which is a spin zero particle, which looks like a band here, corresponding to its mass. This goes through a phi, which is a spin one particle, so you have a node here, and I don't remember which one is it, the F2 here, which is a spin two particle, so you have two nodes, one here and one here. So the number of nodes corresponds to the spin of the particle. And this is interesting because, well, sometimes you can spot the contribution by eye. In this case, for instance, this is clear phi, spin one node, the mass corresponds to the mass of phi. This here is the K star, 892, again, spin one with a node here, very, very wide. In this case, it's a bit of a mess, so you can have many different contributions. You can have interference between different states. So it's not always clear by eye. And the important thing is that this contributions can actually can simulate real resonant peaks where there are actually no resonances. So for instance, this is the D to KK pi decay. And if you have a look at the K plus pi plus invariant mass, you actually see two peaks. So these are not actual resonances. This is what happens when you project the two bands of the phi, and you get two different peaks. Okay? But this is actually a phi, and you can actually see it from this other projection. So by only looking at 1D projection, you're not able to discriminate the full contribution you can have. If you have dozens of contributions in a state, by looking at the invariant mass, it's just not enough. So you need an amplitude analysis to try to discriminate all of them. And so this is important because when you spot a new state, a new exotic state, you need to make sure it's not a reflection in a Daleks plane. Yeah. So given this, we have basically two different models, well, two different methods to study exotic resonances. First one is a full amplitude analysis, of course, which is a coherent sum of all the possible contributions that can enter in the mass in the decay chain, which takes into account also phases and interferences, and from which you can extract all the properties of single particles. But of course, it's computationally very expensive. It's difficult. Takes a lot of time. So sometimes we can also go with this, just a modal independent analysis, which is based on the Legendre polynomial expansion, which I will talk about a bit later. This is basically only assumes very general information on what are the possible particles that can decay into a given final state. And with this method, we can only say if the spectrum we see can be explained through reflections or not. Yeah. So it does not extract any kind of information about what is actually in the decay chain, but if the data can be described by reflections, means that there's no need for an exotic contribution. So let's start with the first character, the first very important exotic candidate. That's the X30X72. That's the first well-established exotic candidate ever discovered by the Bell experiment in 2003, which is this peak here in the red square. This is a narrow peak in the GFAE pi invariant mass from P to K GFAE rho decays. And this was actually observed in the following years than many other many other experiments, including LHCb. This is the same plot as this one, but 10 years later. So the peak is it's much larger, much more well defined, if you wish. And the mass of this state is very close to the KC12P expected charmonium state, but the width is extremely small. And actually up to last year, we only had an upper limit on the width. And the radiative decay to the KC1 state is not seen, and that is expected to be large if the XT72 is a charmonium. And another suspicious thing is that the mass of the X is really close to the D0, D star 0 threshold. So it could be that this X is a D0, D0 star bar molecule, which can exchange pions, and the D0 and D0 star can exchange pions. So its radius will be very large. So given its mass, this interpretation is most logical. However, there are many indications that this is not actually the case. For instance, the decays to Psi2S gamma are supposed to be suppressed with respect to the ones to GFAE gamma if the X is a molecule, but you can actually see that they are not suppressed, and this favors the pure molecular model interpretation. And another thing is that, as I said, the binding energy is very small because the mass of the X is very close to the star threshold. So if the binding energy is small, it means that the molecule is very large, and the relative momentum between two components is very low. And this cannot, you cannot have high production cross-section at high PT, because there's not enough energy for the molecule to remain binded if you have high PT, which is in contrast with what we observed. This is actually a plot of the ratio between the X3872 and the Psi2S reduction cross-section as a function of the event multiplicity, which is again a function, well, it's correlated with PT, of course. Then the quantum numbers have been measured by LHCb in 2015. This is an angular analysis of what we call the golden channel, GFAE rho, and found out that this has JPC equals to 1 plus plus. All the other assignments are rejected with more than 16 sigmas. And this is actually, these quantum numbers are expected for a state with compact size. So again, a molecular interpretation is disfavored. So all of this points towards a compact tetraquark. And just to add wood to the fire, both Babar and Best3 observed the X to JPsi omega decay. And the problem is that JPsi omega and JPsi rho have different isospins. So we know for sure this is not charmonium, but if this is a compact tetraquark, we might have different particles decaying into JPsi rho and JPsi omega with a very close mass. So there could be the two isospin partners that I was talking about. The problem is that we don't know for now, so we haven't observed any of the isospin partners of the X, and we're not able to say that this is actually the same particle or not. So, one last thing. This is something that came out just last year. This is a study of the analytic structure of the X near the D0 star threshold. It's basically a study of the line shape of the X from an amplitude fit. And if you just lower the amplitude in the Riemann plane, if you remember that the square root, the complex square root looks like this in the Riemann plane. So there's two planes intersecting each other. You actually see that there are two poles using the Flatey amplitude for the DD star channel. One, which is this one, is on the physical sheet. The other one is on the unphysical sheet. So this is not interesting. But this one is actually very close to the line where the imaginary part of the energy is zero. And actually, if you take the pole and basically you project the coupling to all the other possible channels to zero, the pole goes exactly there. So you see that in the end, coming from here, it goes here, and that means that the energy is negative. The bonding energy is negative, so this is actually a bound state. Okay. So the virtual assignment cannot be ruled out, but bound state assumption is preferred for now. Okay. So what we know from this analysis is a very complex analysis, and we know that the X is very likely a bound state, so it's not just a virtual state or a kinematic artifact, but still we don't know what exactly it is. And actually, this is just a summary of all the measurements that have been done. So on the left, that's the mass, and on the right, the width. And you can actually see that LHCb measured the width to be non-zero. This actually happened last year. There were two analyses, both measuring the width of the X. And the mass, which is still very close to the blue point here, is the D0 star threshold. So we cannot tell if it is above or below threshold, but it's very close. So we are closing on that, hopefully. So after 20 years, we still don't know anything about the state, basically. Well, we know it's not a pure charmonium. We know it's not a pure molecule. It's probably not also a compact tetraquark. There are indications that it might be a mixture between a molecule and a charmonium state, but there's no general consensus, so we need to investigate more. And this is just something that I'm going to tell you, but don't tell anybody. There are currently about 10 analyses in LHCb, which are planned or ongoing, just to measure the properties of this state. So this is a very important state in the exotic spectroscopy field. Okay, so let's move to something maybe more strange. This is a plot of the Psi2S pi invariant mass from 2008 by the Bell experiment, where you can actually see this nice peak here, which they claim is from the Z4430 minus state. Okay, so that's a charged exotic state with this minimal content, c-cbar, du bar. Then Baba did the same analysis, but they couldn't see anything, and they did what I was explaining for the Legendre polynomial expansion, and they just realized that they could explain the whole spectrum by just using reflections in the K-star system. So LHCb did the same thing. So the Legendre polynomial expansion, can tell you something about it now. Basically, you need to describe the 2D plane. In this case, it's the K-pi mass and the K-star helicity angle, and you expand the helicity angle in Legendre polynomials. That's the expansion. You can extract this AL coefficient from data, and the L max that you see here is actually double the total angular momentum, which is 4 in this case. And the total angular momentum, you need to actually, that's the only assumption you have to do. So you basically say that in this decay, given the kinematics, given the mass constraints and everything, you expect that only resonances up to spin 2 exist in this decay. And then you can have an analytical, if you wish, description of the mass, where it is evident that there's a structure here which is not described by this prediction. Yeah. So this is an additional contribution. So we know that the reflections in the K-pi system, in the K-star system, cannot explain the spectrum. And there we go with an analysis, with an amplitude fit. So in the amplitude fit, you use all the known K-star resonances as bright bigness. This is specifically a 4-dimensional fit, and you can actually see that I forgot to put legend here, but the red line is the full fit. Well, this other line here, the brownish, I think, is the fit without any exotic contribution. So you really need a Z4430 to explain the data. And furthermore, you can, of course, you can measure the quantum numbers, and in this case, which are found to be 1 plus. And on top of that, as any resonance, when you cross the, well, when you scan the mass of the resonance, you expect a rapid change in phase just when you pass below the peak. Yeah. This is true for any resonant phenomenon in all fields of physics. And if you draw the phase, and this is which is called the Argand plot, so this is just the imaginary part and the real part of the amplitude, what you expect is a circle when the resonance is happening. And this is exactly what we observe. So this is a confirmation that that state is an actual resonance. Yeah. And so this is the first unambiguous observation of a charge in Pentaquark. Now, this state is observed again by Bell, but not by Baba in the GFAE pi channel. Baba is just denying things, apparently. But there was a paper suggesting a larger wave function overlap to the psi2s to explain the preferential coupling. Yeah, so again, this is the Bell on the left and Baba on the right, where you can explain everything by Legendre polynomials. So again, let's do it in LHCb with the Legendre polynomials. This is actually a slightly more complicated version. It's called the Legendre Moments. It's the same idea, but a bit more complex. And again, we only use the highest spin of the k-star contribution that we expect to be there, based on the mass. So there's actually a different contribution given the different mass thresholds. And in this case, depending on the mass slice, we have k-star resonances up to spin 3. Yeah. So what we do is to take the 4 solid angles that univocally defines the decay for a given k pi pair, well, k pi invariant mass slice, with again this theta b is the Elizabeth angle of the k star, and then you can expand the differential decay rate this way with this f y, which is a combination of spherical harmonics, so it's just an orthonormal basis, and then this gamma are the Legendre moments, which are extracted from data just like the Legendre polynomials. Yeah. But it's a bit more complex, but the core idea is the same. And this gives, okay, this gives, so on the plot on the left here, this is exactly at the k star 892 peak. So you see that everything is well described by moments up to j equal 2, which is expected because there's this region of mass is dominated by the k star. But if you go to the higher mass slice, this doesn't work anymore. Okay, so the red curve here is the j equals to 2 maximum momentum, angular momentum. And the blue one is j equal 15, which is of course unphysical, but that is used as a baseline to calculate significance. Yeah. So of course we don't expect resonances of spin 15 here. This is just a mathematical artifact to get an unbiased distribution for significance calculation. So yeah, you can clearly see that there are regions here which are not well described by the red curve. And we need probably exotic contributions here as well. Okay, so let's move to something again even more interesting, which is the analysis of this decay, which is lambda b to j psi k proton. This was done in 2015 with the run 1, the LHCb run 1 dataset, and from just by plotting the data with a phase-space distribution in red overlaid, you can clearly see that there's something going on in both the K proton and the J psi proton systems. In this decay chain, of course, you expect a lot of excited lambda to K proton decays to dominate the shape of the mass spectra, which is basically this Feynman diagram here on the left. Although you can actually also have something like this, where this PC state is what we now know as Pentaquark. So let's have a look at what we did. This is again a full amplitude fit with 14 well-established excited lambda. Sorry, no, lambda, it's gamma. No, that's lambda. That's lambda. To PK. And there's the list of all the resonances that have been included in the fit. The fit is a 6-dimensional fit with 5 angles and the K protein binding mass with helicity formalism and background subtracted data. So this is the fit to the lambda b, from which we extract the signal, which is basically just the red shape here, and the Dalitz plot, which you can observe, is the background subtracted Dalitz plot on the right. And you can see clearly band here, vertical band here, which is where the first excited lambda lie, and some interesting band in this direction as well. Yeah. So by forming an analysis fit, amplitude fit, sorry, you see on the left, well, you have by only including excited lambda states. On the right is what you get if you also include 2 additional new PC plus states, just this magenta here and blue here, which can cover nicely, so to speak. So in the end, we get these 2 states, one with JP 3 halves minus, the other one 5 halves minus. One is quite large, so that's quite large width. The other one is a bit narrow with large significance. So this is actually the first observation of something that might be a 5-quark state. Now we can also, well, we can confirm this also again with the Legendre Moments method. I'm not going into details on this, but basically you see that you cannot describe this only by reflections and method. You are experts on the method by now. But there's something else that needs to be checked, which is the rescattering, because you can actually have something like this. You can have a lambda b that decays into an excited lambda star and a KC1. Lambda star goes to the K and the proton, but the proton interacts again with the KC1 and goes to a proton and J psi. And this interaction can actually create an artificial peak, which is basically like a kinematic enhancement due to this effect. In order to have this, all intermediate particles must be on shell, and the lambda star mass must lie within a kinematically allowed range. And we just happen to have one lambda star exactly in this allowed mass range, which could produce this kinematic enhancement. So we actually have 2 methods to disprove that this is the case. First one is to observe the Pentaquark candidate in KC1P, which would confirm the resonant nature of the state. Or we could observe the same Pentaquark in the J psi P pi decay, so the completely suppressed version of the same decay. Because in this case, we're not dominated anymore by lambda stars, but by N stars. And there are no N stars that lie within that kinematically allowed mass range. So this will be much harder to accommodate. So this is the analysis of the completely suppressed decay. Again, that's an amplitude analysis using all the known N stars to P pi excited states. Again, 6-dimensional fit with helicity formalism and background subtracted data. You can see the lambda b peak here. And actually, not only we observe both pentaquarks, but also another another charged Pentaquark candidate for free. So the production rates are what we expect from the previous observation, including, of course, the Capriotti suppression. So we have a combined significance of 3.1 sigma for both states, which confirms that they are not due to scattering, but they are indeed true resonances. Then what happened in 2019, people decided to repeat the Pentaquark analysis using the full run 1 and run 2 data set. So it's about 9 times more statistics with respect to the previous analysis. You can see here on the right, that's the full run 1 and 2 data set with respect to the old one. And you can already see here that there's something strange, because this band here, there's actually another one here. It looks a bit different. Okay, so what happened is that we can actually now, we have enough resolution to resolve the old peak into 2 different peaks. They're very narrow. You cannot see it very well here, but I'll show it in a bit. And another one pops out just here, which was not there before. An amplitude fit for this state is very expensive computationally. So it is ongoing, but it's not easy. But the problem is that they are very narrow. So all 3 states are very narrow, so they cannot be reflections. Reflections by nature are quite wide. So it is enough just to perform a full one-dimensional fit, just to start having a look at their masses and widths. And of course, this analysis is not sensitive to any broad contribution as in the previous analysis. So what we have are exactly 3 states. This is a completely new state, and this is the old state, which is now resolved into 2 peaks. And the interesting thing is that they are all just below the mass threshold, in this case for lambda c d0, and in this case for lambda c d star, which is exactly what you would expect for a molecule. So of course, we need to measure the quantum numbers and try and find isospin partners. So there's a lot of work to do this, but this is for now very striking that we have 2 mass thresholds here, and we have the only states that we observe are exactly there. Now, this is just something that happened last year. Just wanted to give some very fresh results, and this is actually a very important result as well, because by looking at the JPSI spectrum of this prompt JPSIs, so JPSIs which are produced in the PP interaction, and decay both into muon pair, we actually observe a strange structure just here. This strange structure here, which cannot really be explained by a pure background model. In this case, the background model includes 2 contributions. One is called DPS, which is double Parton scattering, when you actually have two JPSIs from 2 different interactions, or the non-resonant single Parton scattering. So we have 2 JPSIs from the same interaction, and they are in green and magenta in this plot, respectively. In this case, you cannot really describe the data with this background description. So we actually have 2 different explanations for this structure. They both require at least one resonance, and which is this one here at 6,900 MeV, and same thing here. But then the problem is to describe the enhancement threshold. We can do it both with another pair of resonances, which you can see here on the left, or with interference between the new resonance we have and the single Parton scattering background, where this resonance is also supposed to come from. So we cannot distinguish between, they're both very good descriptions of data, so we have no means to disentangle them. What we know is that there's definitely a new resonance here, Okay? And if this state is confirmed, this will be a first observation of an exotic resonance, which is entirely composed by heavy quark, and not only entirely composed by heavy quark, but heavy quarks of the same flavor. So this will be a 4-charm tetraquark. Yeah. So this is quite interesting. It's the first time we actually observe a 4-charm tetraquark. This has huge impact on, especially on, on theoretical models on the binding mechanisms that we can have for exotic particles. Because in this case, everything has the same mass, so it's all the same. So it dramatically simplifies the binding mechanisms, the methodology to get binding mechanisms. So this is great for the future of exotic spectroscopy. Now, I'm just going to the conclusions. So the exotic spectroscopy is, I hope I showed you, is an extremely rich and productive field. We have discovered more than 25 new states from 2003. There have been observation and searches of pentaquarks in the last years, which is something that we couldn't actually predict maybe 5 or 6 years ago. This is quite a recent discovery, so it's just the beginning of a new era of discoveries and in understanding really how QCD works. This is just pure QCD binding. So we don't know yet what the real nature of all these states is. We don't know if they're compact multiquarks, compact tetraquarks, compact pentaquarks. We don't know if they're molecules or they could be something even more complex. We just don't know. And I just want to point two things that the LHCb run-to update on pentaquarks is the strongest evidence towards the existence of molecular states, in this case baryonic molecules. And the 4-charm state that I just talked about is the strongest evidence for compact tetraquark. Yeah. So it looks like we're going somewhere. Something that I didn't tell you is that there are actually a lot of exotic candidates also in the BB bar, in the c-bar and the c-bar, and also in light spectra. Yeah. So there's a lot of exotic candidates. Not all of them are confirmed. Usually some of them are found to be conventional candidates or just kinematic reflections, kinematic enhancements. But we know that there's something there. So this is just the tip of the iceberg because there's so many things that we need to understand about exotic particles yet. I just want to say goodbye by showing you this. This is the list of the c-cbar resonances as of 2020, actually not 2019 because there was an update. So this is the list of all the c-cbar states from the PDG, and this is the red ones are the exotic candidates. So basically, half of the charmonium spectrum today is composed by exotic candidates. So there's a lot to do, and probably we'll have a lot of surprises also in the BB bar spectrum where the environment is even cleaner than this. Yeah. And yeah, that's it.